Introduction to MASQUE. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into MASQUE, which stands for Multiplexed Application Substrate over QUIC Encryption. This is a relatively new protocol framework that is revolutionizing how we think about proxying and tunneling traffic in modern networks. MASQUE builds on top of QUIC, which itself is already a significant advancement in transport protocols. The key innovation here is that MASQUE creates a standardized way to tunnel arbitrary traffic through QUIC connections, providing both the performance benefits of QUIC and the flexibility of HTTP semantics. The name itself tells us a lot about what this protocol does. The word multiplexed indicates that multiple streams of data can be handled simultaneously over a single connection without head-of-line blocking. Application substrate means it provides a foundation upon which applications can build their networking capabilities. And of course, QUIC encryption emphasizes that all of this happens over the encrypted and modern QUIC transport protocol. This combination is particularly powerful because it addresses several pain points in traditional VPN and proxy architectures. MASQUE is not just one protocol but rather a family of protocols defined by the IETF in multiple RF circa S. The main components include Connect UDP for proxying UDP datagrams, Connect IP for proxying IP packets, and HTTP datagram for carrying unreliable data. Together, these create a flexible framework that can handle everything from simple HTTP proxying to full VPN-like tunneling scenarios. The protocol is designed to work seamlessly with HTTP/3, which runs on top of QUIC, making it a natural fit for modern web infrastructure. The evolution from traditional proxies. To understand why MASQUE matters, we need to look at how traditional proxy protocols work and what limitations they have. The classic HTTP connect method has been the standard way to tunnel TCP connections through an HTTP proxy for decades. When you use connect, you're essentially asking the proxy server to create a direct TCP connection to a destination server on your behalf, and then the proxy just blindly forwards bytes back and forth. This works fine for HTTPS and other TCP-based protocols, but it has several significant limitations. First, traditional TCP connect only works with TCP in today's world. UDP is increasingly important, especially with protocols like QUIC, WebRTC, and DNS over HTTPS. There was no standard way to proxy UDP traffic through an HTTP proxy. Second, Connect creates a dedicated connection for each tunneled stream, which means you lose the multiplexing benefits that HTTP/2 and HTTP/3 provide. Third, the proxy has no visibility into what's being tunneled, making it difficult to apply policies or perform any intelligent routing decisions. VPN protocols like OpenVPN, WireGuard, and IPsec solve some of these problems by operating at the IP layer, but they come with their own challenges. They typically require special client software, dedicated ports that might be blocked by restrictive firewalls, and they don't integrate well with standard web infrastructure. More importantly, they often struggle with performance in high latency or lossy network conditions because they're built on older transport protocols that suffer from head-of-line blocking. MASQUE takes a different approach by building on QUIC and HTTP/3. QUIC already solves many transport layer problems with features like native multiplexing, improved loss recovery, and built-in encryption. By layering proxy functionality on top of QUIC through HTTP/3, MASQUE gets all these benefits while maintaining compatibility with existing HTTP infrastructure. Firewalls that allow HTTPS traffic will typically allow MASQUE traffic since it looks like normal HTTP/3. This is a huge advantage for deployability compared to traditional VPN protocols. QUIC Foundation. Before we dive deeper into MASQUE, we need to understand QUIC, the transport protocol that makes MASQUE possible. QUIC was originally developed by Google and later standardized by the IETF. It is designed to be a faster, more secure alternative to TCP plus TLS. One of the most important features of QUIC is that it runs over UDP at the transport layer, which gives it flexibility that TCP-based protocols do not have. This might seem counterintuitive since UDP is traditionally thought of as unreliable, but QUIC implements its own reliability mechanisms on top of UDP. The key innovation in QUIC is stream multiplexing without head-of-line blocking. In HTTP/2 over TCP, if one packet is lost, all streams have to wait for that packet to be retransmitted, even if the lost packet only affected one stream. This is called head-of-line blocking, and it's a fundamental limitation of TCP. QUIC solves this by managing multiple streams independently within a single connection. If packet loss occurs, only the affected stream needs to wait for retransmission while other streams continue to deliver data. This results in better performance, especially on high latency or lossy networks. Another crucial feature of QUIC is connection migration. With TCP, a connection is identified by the four-tuple of source IP, source port, destination IP, and destination port. If your IP address changes, like when you switch from Wi-Fi to cellular, the TCP connection breaks and needs to be re-established. QUIC uses connection IDs instead, which are independent of network addresses. This means a QUIC connection can survive network changes seamlessly, making it ideal for mobile devices and other scenarios where network paths change frequently. QUIC also integrates encryption as a core component rather than an optional layer. All QUIC packets are encrypted, and the encryption handshake is combined with the connection establishment handshake. This reduces the number of round trips needed to establish a secure connection compared to TCP plus TLS. Additionally, QUIC encrypts almost all protocol metadata, including packet numbers, which provides better privacy and makes it harder for middleboxes to interfere with the connection. These properties make QUIC an excellent foundation for modern proxy and tunneling protocols like MASQUE. MASQUE protocol components. MASQUE is actually a suite of related protocols, each designed to handle specific types of traffic. The primary component is defined in RFC 9298, which specifies how to proxy UDP datagrams using the HTTP connect UDP method. This is the most fundamental building block because UDP is used by many modern protocols, including QUIC itself, DNS, WebRTC, and various gaming and streaming applications. The connect UDP method works similarly to the traditional connect method, but specifically for UDP traffic. When a client wants to proxy UDP traffic, it sends an HTTP request with the connect UDP method to the MASQUE proxy. This request includes the target host and port where the UDP traffic should be forwarded. The proxy responds with a success code if it is willing to proxy the traffic, and then the client can begin sending UDP datagrams encapsulated in HTTP datagram frames. These frames flow over the QUIC connection to the proxy, which decapsulates them and forwards them as normal UDP datagrams to the target destination. The second major component is Connect IP, defined in RFC 9484, which allows proxying of IP packets. This is more powerful than Connect UDP because it works at the IP layer, meaning it can tunnel any IP protocol, not just UDP and TCP. This makes it suitable for creating VPN-like functionality where the entire IP stack of a client device can be tunneled through the proxy. With Connect IP, a client can send IP packets of any type, and the proxy will forward them to their destination, effectively creating a point-to-point IP tunnel. HTTP datagram, specified in RFC 9297, is the underlying mechanism that enables both Connect UDP and Connect IP to work. It defines how to carry unreliable datagrams within HTTP/3 connections. Unlike traditional HTTP request-response semantics, Datagrams are fire and forget messages that do not have guaranteed delivery or ordering. This is perfect for applications that already handle their own reliability, like QUIC running over MASQUE, or applications that prefer low latency over guaranteed delivery, like real-time video or gaming. The datagram frames are multiplexed with regular HTTP streams on the same QUIC connection, giving you the best of both worlds. Connect UDP Deep Dive. Let's examine Connect UDP in detail because it is the most commonly used MASQUE component. The Connect UDP method extends HTTP with a new request method specifically for establishing UDP proxy tunnels. When a client wants to proxy UDP traffic to a specific destination, it sends an HTTP request with the method set to connect UDP, and includes the target host and port in the request headers. The request looks like a normal HTTP request but with special semantics that tell the proxy what UDP endpoint should receive the forwarded traffic. The proxy server receives this Connect UDP request and makes a policy decision about whether to allow the proxying. It might check authentication credentials, verify that the target destination is allowed, check rate limits, or apply any other business logic. If the proxy decides to allow the request, it responds with a 2xx success status code, typically 200 OK at this point. The proxy has established the UDP forwarding context, and it is ready to handle datagrams for this tunnel. The HTTP stream that carried the Connect UDP request remains open and is used as the control channel for this proxy session. Once the tunnel is established, the client can begin sending UDP datagrams. These are encapsulated in HTTP datagram frames, which include a datagram flow identifier that associates them with the correct Connect UDP tunnel. The proxy receives these datagram frames on the QUIC connection, extracts the UDP payload, and sends it as a regular UDP datagram to the target destination. When the target sends UDP datagrams back, the proxy receives them, encapsulates them in HTTP datagram frames, and sends them back to the client over the same QUIC connection. One important aspect is how Connect UDP handles the mapping between QUIC streams and UDP flows. A single QUIC connection can carry multiple Connect UDP tunnels simultaneously, each identified by the HTTP stream ID that carried the initial Connect UDP request. The datagrams for each tunnel are tagged with the corresponding flow identifier, which allows the proxy to correctly route them to the appropriate target. This multiplexing capability means a client can proxy UDP traffic to multiple destinations through a single QUIC connection to the proxy, which is much more efficient than maintaining separate connections for each destination. Connect IP for Layer 3 tunneling. While Connect UDP is great for proxying specific UDP flows, Connect IP takes things to the next level by operating at the IP layer. This means it can tunnel entire IP packets, regardless of what transport protocol they use. This is the component that enables true VPN-like functionality with MASQUE. When you use Connect IP, you are essentially routing all IP traffic from a client device through the MASQUE proxy, which then forwards it to the internet on the client's behalf. The Connect IP request is similar to Connect UDP, but with some important differences. When establishing a Connect IP tunnel, the client typically negotiates the IP address it will use inside the tunnel. The proxy might assign the client a specific IP address from a pool it manages, or in some configurations, the client might request a specific address range. This IP address configuration is crucial because it determines how routing works inside the tunnel and how return traffic finds its way back to the client. Once the Connect IP tunnel is established, the client can send complete IP packets encapsulated in HTTP datagram frames. These packets include the full IP header with source and destination addresses, protocol field, and all the normal IP metadata. The proxy decapsulates these packets and forwards them based on the destination IP address in the packet header. This is different from Connect UDP where the target is specified in the initial request. With Connect IP, each packet can have a different destination, just like in a traditional vPages N. The power of Connect IP becomes apparent when you consider use cases like accessing a corporate network from a remote location. A client can establish a Connect IP tunnel to a MASQUE proxy inside the corporate network, and then send IP packets for corporate resources through that tunnel. The proxy forwards these packets into the corporate network, receives responses, and sends them back through the tunnel to the client. From the client's perspective, it is as if they are directly connected to the corporate network, but all traffic is encrypted and multiplexed over a single QUIC connection that looks like normal HTTPS traffic. HTTP Datagram Framework. HTTP datagram is the foundational mechanism that enables both Connect UDP and Connect IP to function. It provides a way to send unreliable, unordered messages within HTTP3 connections. This might seem strange at first because HTTP is traditionally all about reliable request-response exchanges, but datagrams are essential for efficiently carrying UDP and IP traffic. The datagram extension adds new frame types to QUIC that carry these messages alongside regular HTTP streams. The key concept in HTTP datagram is the quarter stream ID. Each QUIC stream that establishes a context for datagrams, like a Connect UDP or Connect IP tunnel, has a stream ID. The datagram frames include this stream ID to associate them with the correct context. This allows a single QUIC connection to carry datagrams for many different tunnels simultaneously. When the proxy receives a datagram frame, it looks at the quarter stream ID to determine which tunnel the datagram belongs to, and then processes it accordingly. HTTP datagram frames can be of arbitrary size, up to the maximum datagram size supported by the QUIC connection. This is important because different networks have different MTU sizes, and the datagram mechanism needs to accommodate this. The sender is responsible for ensuring that datagrams fit within the path MTU, otherwise they might be dropped by the network. MASQUE implementations typically use QUIC/SDPLP-MTUD, which stands for Datagram Packetization Layer Path MTU Discovery, to determine the optimal datagram size for the current network path. One interesting aspect of HTTP datagram is how it handles congestion control. Since datagrams are unreliable by design, they are not retransmitted if lost. However, they still count against the QUIC connection's congestion window. This means if you send too many datagrams too quickly, the QUIC connection will become congested, and even reliable HTTP streams sharing the same connection will slow down. This creates an implicit backpressure mechanism that prevents datagram-heavy applications from starving other traffic on the same connection. Applications need to be aware of this and implement their own rate control if they are sending high-volume datagram traffic. Security and authentication. Security is paramount in any proxy or tunneling protocol, and MASQUE benefits from QUIC's strong security foundation. All QUIC connections are encrypted using TLS 1.3, which means all MASQUE traffic is encrypted end-to-end between the client and the proxy. This encryption protects the tunneled traffic from eavesdropping and tampering as it travels through the network. However, encryption is just one part of the security picture. MASQUE also needs robust authentication and authorization mechanisms to control who can use the proxy and what destinations they can access. Authentication in MASQUE typically uses standard HTTP authentication mechanisms. The most common approach is to use HTTP authentication headers, like authorization, with bearer tokens or basic authentication. When a client sends a Connect UDP or Connect IP request, it includes authentication credentials in the request headers. The proxy validates these credentials before establishing the tunnel. This authentication can be tied to existing identity systems, making it easy to integrate MASQUE proxies into enterprise environments with centralized user management. Beyond authenticating who is using the proxy, authorization controls what they can do with it. A proxy might allow certain users to access only specific destination addresses or ports, implement rate limiting based on user identity, or apply different quality of service policies for different users. These authorization policies are typically configured on the proxy server and enforced when connect requests are received. The proxy can also monitor ongoing tunnels and terminate them if they violate policies, such as exceeding bandwidth limits or attempting to access forbidden destinations. An important security consideration is preventing open proxy abuse. An improperly configured MASQUE proxy could be exploited to proxy traffic to arbitrary destinations, potentially being used for attacks or to hide malicious activity. To prevent this, proxies should implement strict destination allolists, validate that connect requests are from authenticated users, implement rate limiting and traffic monitoring, and log all tunnel establishments for audit purposes. Some deployments also use mutual TLS authentication where both the client and proxy authenticate to each other using certificates, providing even stronger security guarantees. Performance characteristics. One of MASQUE's biggest advantages is the performance characteristics it inherits from QUIC. Traditional TCP-based proxies and VPNs suffer from head-of-line blocking, where the loss of a single packet can stall all traffic on a connection until that packet is retransmitted. QUIC's stream independence eliminates this problem. If a packet carrying data for one connect UDP tunnel is lost, it doesn't affect other tunnels on the same connection. This is particularly beneficial when proxying multiple UDP flows simultaneously, as is common in real-world deployments. Connection establishment is also significantly faster with MASQUE compared to traditional VPNs. A QUIC connection can be established with a 1 RTT handshake in most cases, or even 0 RTT if the client has previously connected to the server and has valid session tickets. Compare this to OpenVPN or IPsec, which typically require multiple round trips to negotiate parameters and establish the secure tunnel. The faster connection establishment means applications can start sending traffic sooner, improving the user experience, especially for short-lived connections. MASQUE also benefits from QUIC's improved loss recovery algorithms. QUIC uses a more sophisticated approach to detecting and recovering from packet loss compared to TCP. It maintains separate packet number spaces for different encryption levels and uses more accurate loss detection timers. This results in faster recovery when packets are lost and better throughput in challenging network conditions. For proxy and VPN use cases where the path between client and proxy might traverse multiple networks with varying quality, this improved loss recovery is crucial. However, MASQUE is not without performance costs. There is inherent overhead in encapsulation and decapsulation of datagrams. Every UDP datagram or IP packet needs to be wrapped in HTTP datagram frames, which adds headers and requires processing on both the client and proxy. For high bandwidth applications, this overhead can become significant. Additionally, running UDP inside QUIC inside UDP creates what is sometimes called a double UDP problem, where QUIC's congestion control operates on the outer QUIC connection, while the inner UDP flows might have their own rate control. Careful tuning is needed to ensure these layers work together efficiently, rather than fighting each other. Deployment architectures. MASQUE can be deployed in several different architectural patterns depending on the use case. The simplest deployment is a forward proxy, where clients in a network use a MASQUE proxy to access external resources. This is similar to traditional HTTP proxies but with support for UDP and IP tunneling. The proxy sits at the edge of the organization's network, and clients direct their connect UDP or connect IP requests to it. This architecture is useful for scenarios like providing internet access to clients while maintaining centralized control and monitoring. Another common architecture is the reverse proxy or ingress model. In this setup, the MASQUE proxy is deployed at the edge of a service provider's network, and clients from the internet connect to it to access services behind the proxy. This is particularly useful for scenarios like providing access to services that primarily use UDP protocols. For example, A gaming service might deploy MASQUE proxies to allow clients to connect to game servers through QUIC, getting better performance than traditional TCP-based proxies while maintaining the ability to apply access control and DDoS protection. The VPN use case typically involves a hub-and-spoke architecture where multiple clients establish connect IP tunnels to a central MASQUE proxy. The proxy acts as the VPN gateway, routing traffic between clients and the internal network, or between clients and the Internet. This architecture can replace traditional VPN solutions while providing better performance and easier deployment. Since MASQUE traffic looks like normal HTTPS, it is less likely to be blocked by restrictive firewalls compared to traditional VPN protocols that use dedicated ports. More advanced deployments might use a multi-hop architecture where MASQUE proxies are chained together. A client connects to a first-level proxy, which then establishes a Connect UDP or Connect IP tunnel to a second-level proxy, and so on. This creates a more complex routing path that can provide additional privacy or allow traffic to traverse multiple network boundaries. Each hop adds latency and overhead, so this architecture is typically used when the routing complexity provides specific benefits, such as geographical distribution or jurisdictional boundaries. The multi-hop approach also provides better resilience, as the path can be rerouted if any intermediate proxy fails. MASQUE versus traditional VPN protocols. When evaluating MASQUE against traditional VPN protocols like OpenVPN, IPsec, and WireGuard, we need to consider multiple dimensions, such as performance, deployability, security, and use case fit. OpenVPN has been the gold standard for VPNs for many years. It is highly configurable, supports both TCP and UDP transport, and has wide platform support. However, OpenVPN shows its age in a few ways. It uses TLS for encryption, which adds overhead, and when running over TCP, it suffers from the TCP over TCP problem, where the inner and outer TCP congestion control algorithms can fight each other, which leads to poor performance. IPsec is another mature VPN technology that operates at the network layer. It comes in two modes: transport mode, which encrypts only the payload, and tunnel mode, which encrypts the entire IP packet. IPsec is very efficient because it operates in kernel space and has hardware acceleration support in many devices. However, IPsec is notoriously complex to configure, especially when dealing with NAT traversal. It also uses dedicated protocols like ESP and AH that operate on specific IP protocol numbers, which means they are often blocked by restrictive firewalls and NAT devices. This is why IPsec implementations often include NAT-T, which encapsulates IPsec in UDP, but this adds complexity. WireGuard is the newest kid on the block and has gained tremendous popularity due to its simplicity and performance. It uses modern cryptography primitives, has a tiny codebase that is easy to audit, and achieves excellent performance. WireGuard operates at the network layer like IPsec but with much simpler configuration. However, WireGuard also uses a dedicated UDP port and does not try to hide itself as regular web traffic. This means it can be blocked or deprioritized by network administrators or ISPs. WireGuard also has a controversial aspect in its handling of IP address assignment and its always-on nature. MASQUE offers a different set of trade-offs. Its biggest advantage is that it looks exactly like normal HTTPS traffic. A MASQUE connection is indistinguishable from someone browsing the web or using any other HTTP/3 application. This makes it extremely difficult to block without blocking all HTTPS traffic. MASQUE also benefits from QUIC's performance characteristics, including stream multiplexing and improved loss recovery. However, MASQUE has higher overhead than WireGuard due to its encapsulation layers and HTTP framing. It is also newer and has less deployment experience compared to the mature alternatives. The choice between MASQUE and other VPN protocols often comes down to whether the primary concern is raw performance and efficiency, in which case WireGuard wins, or whether it is about working in restrictive network environments, where MASQUE shines. NAT traversal and connectivity. Network address translation, or NAT, is one of the most common challenges for any peer-to-peer or tunneling protocol. Most home and corporate networks sit behind NAT devices that map private IP addresses to public ones. This creates problems for protocols that need to establish direct connections because the devices behind NAT are not directly reachable from the Internet. Traditional VPN protocols handle this in various ways, but MASQUE's approach is particularly elegant because it leverages the client-server model of HTTP. With MASQUE, NAT traversal is typically not an issue because the architecture assumes a client-proxy relationship rather than peer-to-peer. The client initiates the connection to the proxy, which means the client is making an outbound connection that NAT devices handle naturally. The proxy server needs to be reachable with a public IP address, but that's a standard requirement for any server infrastructure. This is different from peer-to-peer VPN scenarios where both endpoints might be behind NAT, requiring techniques like STUN, TURN, or ICE to establish connectivity. However, there are scenarios where you might want to connect two clients behind different NAT devices using MASQUE as an intermediary. In this case, both clients would establish Connect IP or Connect UDP tunnels to a MASQUE proxy server, and the proxy would forward traffic between them. This is similar to how TURN servers work in WebRTC. The proxy acts as a relay, adding a hop in the communication path but solving the NAT traversal problem. The overhead of this relaying is mitigated by QUIC's efficient multiplexing and the fact that the proxy can handle many client pairs simultaneously on a single port. Another interesting aspect is how MASQUE handles IPv6 transition scenarios. Many networks are still IPv4 only or have broken IPv6 connectivity. A MASQUE proxy can bridge between IPv4 and IPv6, allowing clients on IPv4 only networks to access IPv6 resources by tunneling through the proxy. This is particularly useful as we continue the slow transition to IPv6. The proxy can maintain both IPv4 and IPv6 connectivity, and route traffic appropriately based on the destination address in Connect IP packets or the target specified in Connect UDP requests. Congestion control and quality of service. Congestion control is a critical aspect of any transport protocol, and MASQUE inherits QUIC's sophisticated congestion control mechanisms. QUIC implements pluggable congestion control, meaning different algorithms can be used depending on the deployment scenario. The most common implementations use variants of TCP QUIC or the newer BBR algorithm. BBR, which stands for bottleneck bandwidth and round-trip propagation time, is particularly interesting because it tries to operate at the optimal point where the network pipe is full but not overflowing, reducing buffer bloat and improving latency. When you tunnel traffic through MASQUE, you create a layering situation where congestion control operates at multiple levels. The outer QUIC connection has its own congestion control, managing how fast data can be sent between the client and the proxy. If you are tunneling TCP connections through MASQUE using Connect IP, those inner TCP connections also have their own congestion control. This can lead to interesting interactions. The inner TCP might try to increase its sending rate, but if the outer QUIC connection is already at its congestion window limit, the inner TCP will experience packet loss or delay, causing it to back off. This is similar to the TCP over TCP problem but somewhat mitigated by QUIC's better loss recovery. For UDP-based protocols tunneled through MASQUE, the situation is different because UDP does not have built-in congestion control. If you are proxying QUIC connections through MASQUE using Connect UDP, you end up with QUIC over QUIC, which sounds redundant but actually makes sense in certain architectures. The inner QUIC connection manages congestion control for the application's traffic, while the outer QUIC connection manages the tunnel itself. The two congestion controllers can potentially interfere with each other, but in practice, the outer controller operates on aggregate traffic while inner controllers operate on individual flows, so they often work reasonably well together. Quality of service becomes important when multiple applications share a MASQUE connection. QUIC supports stream priorities, which MASQUE can leverage to prioritize certain tunneled traffic over others. For example, in a Connect IP tunnel carrying mixed traffic, you might want to prioritize real-time video calls over file downloads. The MASQUE proxy can examine traffic patterns and apply priorities at the QUIC stream level. However, this requires the proxy to have some visibility into or policies about the traffic it's forwarding, which creates tension with the goal of treating the proxy as a simple forwarding device. Different deployments strike different balances based on their requirements. Privacy considerations and encrypted DNS. Privacy is a multifaceted concern with any proxy or VPN technology. When you use MASQUE, the proxy can see certain aspects of your traffic even though it can't read the content of encrypted connections you make through it. Specifically, with Connect UDP, the proxy knows which host and port you are connecting to because that information is in the connect request itself. With Connect IP, the proxy can see the IP headers of packets you are tunneling, which reveals destination IP addresses. This is similar to traditional VPNs where the VPN server knows your traffic destinations. The question of DNS privacy is particularly important. When you resolve a domain name to an IP address before establishing a MASQUE tunnel, your DNS query might be visible to your local network or ISP even if you then tunnel to that IP through MASQUE. The DNS query has already revealed your intent. This is why combining MASQUE with encrypted DNS protocols like DNS over HTTPS or DNS over QUIC is important for comprehensive privacy. You can actually tunnel DOH or DOQ through MASQUE, creating layers of privacy protection where your DNS queries go through the encrypted tunnel just like your other traffic. An interesting privacy enhancement is using MASQUE to tunnel to another MASQUE proxy, creating a chain. The first proxy in the chain knows your real IP address but doesn't know your final destination because you're just connecting to the second proxy. The second proxy knows your destination but doesn't know your real IP, only the first proxy's IP. This is similar to how Tor works with onion routing, though without Tor-specific circuit construction and guard node concepts. Multi-hop MASQUE chains add latency and complexity but can provide stronger privacy guarantees against traffic analysis. Another privacy consideration is the visibility of MASQUE usage itself. Because MASQUE traffic looks like regular HTTP/3, it is harder for network observers to determine that you are using a proxy or vPages-in. This is both a privacy feature and a potential concern for network administrators who want visibility into their network usage. The trade-off between user privacy and network management is ongoing, and MASQUE sits in an interesting position where it provides strong privacy by default, but can also be deployed with appropriate monitoring and control in enterprise environments through authentication and authorization mechanisms. Implementation challenges. Implementing a MASQUE client or server presents several interesting challenges. The first is correctly handling the HTTP/3 and QUIC stack. While there are libraries available for QUIC, they vary in maturity and completeness. You need to support all the necessary QUIC features including datagrams, stream multiplexing, connection migration, and proper flow control. The HTTP/3 layer adds additional complexity with its stream types, frames, and the QPAC header compression. Getting all these pieces working together correctly is non-trivial. The datagram handling is particularly tricky. The HTTP datagram frames need to be associated with the correct QUIC stream using quarter stream IDs, and the implementation needs to handle the case where datagrams arrive out of order or not at all. The datagram flow ID space needs to be managed carefully to avoid collisions between different tunnels. Additionally, Implementations need to handle the case where the QUIC connection doesn't support datagrams at all, falling back to alternative mechanisms or refusing to establish certain types of tunnels. Use cases and applications. MASQUE enables a wide variety of use cases, some obvious and some quite creative. The most straightforward use case is as a traditional VPN replacement for remote access. An organization can deploy MASQUE proxies at the edge of their network, and remote workers can establish connect IP tunnels to access internal resources. Because MASQUE traffic looks like normal HTTPS, it works even in hotels, airports, and other locations with restrictive firewalls that block traditional VPN protocols. The user experience can be nearly identical to traditional VPNs while having better firewall traversal properties. Another compelling use case is privacy-focused browsing. Privacy-conscious users can run personal MASQUE proxies on cloud servers and route their browsing traffic through them. This is similar to using a commercial VPN service but with more control over the infrastructure. The MASQUE proxy can be combined with other privacy tools like DNS filtering, ad blocking at the proxy level, and traffic analysis prevention. Because multiple users can share a MASQUE proxy, it provides some anonymity within the set of users sharing that proxy, though this is weaker than systems like Tor that are designed specifically for anonymity. Content delivery networks and edge computing platforms can use MASQUE to provide low-latency access to their services. Instead of users connecting directly to edge servers, they can establish MASQUE tunnels that provide consistent, low-latency paths with QUIC's connection migration benefits. If a user moves between networks, the QUIC connection can migrate seamlessly, maintaining active tunnels without interruption. This is particularly valuable for mobile applications that need persistent connectivity as users move between Wi-Fi and cellular networks. Gaming is another interesting use case. Online games often use UDP for game traffic, and MASQUE's Connect UDP capability allows proxying this traffic efficiently. A gaming service could deploy MASQUE proxies geographically distributed around the world, allowing players to connect through the closest proxy for reduced latency. The proxy can also provide DDoS protection for game servers by hiding their real IP addresses and filtering malicious traffic. The QUIC Foundation provides good characteristics for gaming with low latency and fast loss recovery, though the added hop through the proxy does increase latency compared to direct connections. MASQUE in cloud environments. Cloud providers are increasingly interested in MASQUE for various infrastructure use cases. In multi-cloud and hybrid cloud scenarios, organizations need to connect resources across different providers and between cloud and on-premises data centers. MASQUE can provide the interconnectivity fabric for these scenarios. Instead of setting up complex IPsec VPNs or dedicated circuits, organizations can establish MASQUE tunnels between their cloud environments. The HTTP/3 nature of MASQUE means it works through cloud provider firewalls and security groups without special configuration. Kubernetes and container orchestration platforms can use MASQUE for cluster networking. In a multi-cluster deployment, MASQUE tunnels can connect pods across clusters, even when those clusters are in different clouds or data centers. The Connect IP capability provides the necessary Layer 3 connectivity for pod-to-pod communication, while MASQUE's multiplexing allows many pod connections to share a single quick connection between cluster gateways. This can be more efficient than traditional overlay networks that create separate connections for each pod communication. Serverless and edge computing platforms have unique requirements that MASQUE can address. Functions running at edge locations often need to access centralized databases or services. MASQUE can provide efficient tunneling from edge locations back to central regions. The zero RTT connection establishment in QUIC is particularly valuable for short-lived serverless functions that need to establish connectivity quickly. A function can send data on its first packet to a MASQUE proxy using zero RTT, reducing the cold start latency impact of setting up secure tunnels. Cloud-based load balancers and ingress controllers can use MASQUE as a protocol option for backend connections. Instead of traditional HTTP or TCP load balancing, the load balancer can establish Connect UDP or Connect IP tunnels to backend servers. This provides better protocol flexibility, allowing backends to receive UDP traffic or raw IP packets through the load balancer. It also enables scenarios like protocol translation where the load balancer receives traffic over one protocol but forwards it to backends using a different protocol, all while maintaining a single QUIC connection to each backend for efficiency. Monitoring and troubleshooting. Operating MASQUE infrastructure at scale requires comprehensive monitoring and troubleshooting capabilities. The multi-layered nature of MASQUE, with applications running over tunnels running over QUIC running over UDP, creates challenges for traditional network monitoring tools. You need visibility at each layer to understand where problems are occurring. At the application layer, you want to know what applications are using MASQUE tunnels and how much traffic they are generating. At the tunnel layer, you need metrics on tunnel establishment success rates, tunnel lifetimes, and the number of active tunnels. QUIC-level metrics are crucial for understanding transport performance. Key metrics include packet loss rates, retransmission rates, congestion window sizes, and RTT measurements. QUIC's ability to export detailed statistics about stream states and connection parameters is valuable here. The proxy should log when congestion occurs, when connection migration happens, and when connections are closed and why. These metrics help diagnose performance issues and capacity planning. If you see high packet loss rates, it might indicate network path issues or insufficient bandwidth provisioning. Logging for MASQUE needs to balance operational needs with privacy concerns. The proxy should log tunnel establishment events. These events include which user authenticated, what destination they requested, and whether the request was allowed or denied. This audit trail is important for security and compliance. However, logging every packet or datagram would be excessive and raise privacy concerns. A middle ground is to log connection-level statistics periodically. These include bytes transferred, packets sent and received, and error counts. This is done without logging actual packet contents or timing information that could be used for traffic analysis. Troubleshooting tools specific to MASQUE are still evolving. Packet capture tools like TCP dump can capture the outer UDP packets carrying QUIC traffic. But because QUIC encrypts almost everything, you cannot see inside without the encryption keys. QUIC implementations often have key log functionality that exports keys in a format that Wireshark can use to decrypt captured traffic. However, this only works for traffic you control both endpoints of. For production troubleshooting, you often need to rely on application-level logs, QUIC implementation debug output, and synthetic testing where you control both client and proxy to isolate issues. Future directions and standards evolution. The MASQUE working group at the IETF continues to work on extensions and refinements to the protocol suite. One area of active development is improving the efficiency of encapsulation. The current approach of wrapping every UDP datagram or IP packet in HTTP datagram frames has overhead, especially for small packets. There are proposals for more efficient encoding schemes that could reduce per packet overhead, particularly for scenarios like tunneling many small UDP datagrams. These efficiency improvements would make MASQUE more competitive with protocols like WireGuard in terms of raw throughput. Another area of development is better integration with HTTP/3 features. For example, HTTP/3 has a concept of server push where the server can send resources to the client before the client requests them. There are ideas for using similar concepts in MASQUE to optimize certain traffic patterns. A proxy might, for instance, preemptively send data for predictable return traffic patterns, reducing latency. Priority and scheduling improvements are also being explored to better handle the coexistence of regular HTTP requests and tunnel traffic on the same QUIC connection. Standardization of proxy discovery and configuration is an ongoing effort. Currently, clients need to be configured with proxy addresses, authentication credentials, and policies about when to use the proxy. There are proposals for auto-discovery mechanisms where clients can find available MASQUE proxies through DNS or other mechanisms. Configuration protocols that allow proxies to advertise their capabilities, policies, and current load could enable more dynamic proxy selection. This is particularly relevant for scenarios where multiple proxies are available and clients want to choose the best one based on latency, capacity, or other criteria. Looking further ahead, there's interest in combining MASQUE with other emerging technologies. Integration with QUIC multipath, which allows a single QUIC connection to use multiple network paths simultaneously, could provide better resilience and performance for MASQUE tunnels. Combining MASQUE with encrypted client hello, which hides the server name in TLS handshakes, could provide even stronger privacy properties. There's also discussion about how MASQUE relates to other IETF efforts like SRTP and WebRTC, potentially using MASQUE as a tunneling mechanism for media streams. The protocol is still young, and its evolution will be shaped by deployment experience and emerging use cases over the next several years. Conclusion and summary. MASQUE represents a significant evolution in how we think about proxying and tunneling protocols. By building on QUIC's solid foundation and leveraging HTTP/3 semantics, it creates a flexible framework that addresses many limitations of traditional approaches. The key innovations are the ability to tunnel UDP and IP traffic efficiently, the multiplexing capabilities that allow many tunnels over a single connection, and the firewall-friendly nature of appearing as normal HTTPS traffic. These properties make MASQUE well-suited for modern Internet architecture where UDP-based protocols are increasingly important and network paths are often complex. The protocol is not without trade-offs. The encapsulation overhead means that it is not the most efficient option for scenarios where raw performance is paramount, and where dedicated VPN protocols can be used. The relative newness of the protocol means that implementation maturity varies, and deployment experience is still being accumulated. However, for use cases where firewall traversal is important, where multiplexing provides value, or where integration with HTTP infrastructure is beneficial, MASQUE offers compelling advantages. The growing adoption of QUIC and HTTP/3 for web traffic also means that MASQUE can piggyback on that deployment momentum. As we have explored throughout this presentation, MASQUE touches on many aspects of modern networking, from transport protocols and congestion control, to security and privacy, to cloud infrastructure and application use cases. Understanding MASQUE requires understanding QUIC, HTTP/3, tunneling concepts, and how they all fit together. The protocol suite provides building blocks that can be combined in various ways to solve different problems, whether that is simple UDP proxying with Connect UDP, full VPN functionality with Connect IP, or more complex scenarios involving chained proxies and specialized routing. For network engineers, protocol developers, and system architects, MASQUE is worth understanding as part of the modern networking toolkit. As QUIC and HTTP/3 become more prevalent, MASQUE-based solutions will likely become more common for scenarios requiring tunneling and proxying. Whether you're building VPN infrastructure, designing cloud networking, or working on applications that need reliable connectivity across challenging network conditions, MASQUE offers capabilities worth considering. The protocol will continue to evolve based on real-world deployment experience, and staying current with its development will be valuable for anyone working in networking and distributed systems. Thank you for your attendance. Please consider subscribing to the channel.